loading once more and see how that is. Is it gonna go ahead buffer a lot? It would be kind of sad if it does buffer. I mean, in terms of the bit rate, it's kind of maintaining. I mean, that looks kind of good, to be fair. Okay. Perfect. All right. Let's go ahead and start this. Hey there. God. Can you talk? Yeah, I can talk. Can you hear me? I don't remember what was my hotkey for this. Oh, was that? Okay, cool. I figured it out. That's way too thick. Closed sets. Okay, can you hear me? Is that good? Are we good to go? All right. I'll just be moving on, I guess. I think my Discord should be fine. Right? Yeah, we should be fine. I can't. Um, Test. Yeah, that's on you. That's more so you. You. Make sure you're facing. All right. All right. So, God, I haven't done this in a long time, but going ahead, moving forward, with our little definition of close sets. Previously, I guess we could actually just do like a little quick synopsis of what we should have studied beforehand. So I'm gonna go ahead and start from the beginning. So previously, we went over the order topology, which can definitely be fine to study. I mean, it's kind of already given. I mean, if you already know R or like some sort of analytical skills, then you already know what the order topology is to some degree, varying degree. Um, I would say in terms of like like actual point set topology, the order topology is not really used, not really used slash not extremely relevant, not extremely relevant, extremely relevant. Furthermore, I guess the whole idea is more so on product topologies. Product topologies. This one's going to be a huge one, especially later on. Subspace topology. Also going to be huge. And something that hasn't disconnected. That's not good. Okay, cool, cool. I thought I literally lost everything for a second. Something further is going to be your quotient topology, which we haven't gone over yet, but we will. We will in the future. Quotient topology. This is something that we will be going over soon. Didn't we go over quotient topology? No, no, we did not go over quotient topology yet. Quotient topology is, I think, at the end of this chapter. I honestly would have probably addressed this before, but it more so just needs continuity. And it also needs, what else? Kind of like a mix of these two as well. So I kind of just built upon everything itself. We only, from what I understand from your lecture notes and what I watched of the video, you only went over these three topologies itself. And I mean, it's not bad. It's fine. But quotient topology is kind of like the main game changer, especially for like, I guess, using algebraic topology. When we get to algebraic topology, most of it will actually be done in quotient topologies. All right. So let's go ahead and move forward after. Cool. So here we go. So I guess actually starting this sort of lecture, I think we're on I think 17, section 17, close sets and limit points. There we go. So first off, to define a closed set, it's not showing the green thing when I'm talking. Are you sure about that? Hello? It is for me. Wait. It's for me. Hey. Yeah, I couldn't hear you at all. If you Yeah, I don't know. Can you still hear me? That's weird. Oh, you weren't? Okay, cool. All right, I guess we can continue moving on. No, you can't. Is there anyone else facing sort of that problem? No. Check your audio settings. Stream. Stream Discord can hear me. Hello? Yeah, okay. Yeah, stream can hear me fine actually. So yeah, that's kind of a doozy for you, I guess, in the meantime. But where were we? Did we actually, yeah, I did actually go ahead to find that. Okay, cool. Or we do have to actually start defining it. So a closed set, that's not what I wanted. This one, yep. A closed set, given X is a topological space, and then we have the some sort of subset U of X, then U is closed if X minus U is open. And generally with these definitions, I guess something to register if you're kind of new to the whole proof, or I guess like a proof-based mathematics itself, these are always going to be your if and only ifs, always, for definitions, unless stated otherwise. And usually if it's stated otherwise, it's usually like some sort of lemma, theorem, or proposition. Um, so I guess what we've learned from previously is given like a standard topology R, we could actually just take a subset of it. So A to B. Let me just go to the stream. All right. Um, A to B is going to be closed. Um, since we could actually just take the, I guess, the set minus of A to B, which is just going to be your open sets of negative infinity to A, cap B to infinity. So something that I found interesting, especially I guess coming in from an analysis side, that was like I guess the most recent. Generally, whenever we introduce these notions of like I guess infinities itself, especially within the real numbers, it's more so something that we call the extended real numbers. So some people you might actually see, especially in the real world. God, I'm losing my voice. You might see, especially in the real world, the extended real numbers being R joined with plus or minus infinity. And this is what's supposed to replace here. Um, because I guess like in a regular real numbers, these notions of negative infinity and positive infinity being actual, I guess, values can not really exist. Um, but on likewise, we also have A to infinity. I guess we shouldn't actually have it closed. Is also closed. Um, and I thought this was kind of an interesting thing because we could also just take a look at this graph and note that this is true because if we take our set minus this A to infinity, even if it's going to be open on one end, this I guess like sort of indexing, it's still going to have a negative infinity to A as the rest of our open set, which is open. And hence this is going to be closed itself. All right. So given, I guess, this sort of idea, we could go ahead and start establishing a theorem. So previously we've always taken a look at like how, I guess we could just do a quick recall. We've always just taken a look at how all elements in a topology not yet. Let's take a look. So recall that all elements in the topology themselves are going to be open. And so I guess what this does create is I guess we aren't really considering closed sets in general. It hasn't been considering closed sets in general at all. So we're going to go ahead and establish a theorem that goes ahead, considers these closed sets, and I'm just going to go ahead and call this theorem a closed topology. Stream is lagging because 1440p. OBS should be fine. You could decrease the stream quality. Hey Rex, how are you? So given that X is a topological space, X is a top space, then it follows that one, both phi and X, or I guess the empty set and X are both going to be closed, are closed. And we could actually just go ahead and confirm this, because if we do X set minus X, this is just going to be equal to the empty variable, and this itself is open, which we've established previously. And if we go ahead and set X, also take out the empty set, then this is just going to be X, which is also open. So therefore, we know that these two are going to be we just know it doesn't do that actually for I guess sorry, I've just lost my train of thought. I'm kind of responding to text messages. But furthermore, we also have arbitrary intersections of closed sets are closed too. And this is kind of a take on, say, if we also take X set minus the arbitrary unions. So if we do unions of, say, UI, then this is also going to be like, I guess, sort of the same as, I guess, arbitrary intersections of closed sets. So these are self, it's going to be open. So let's just go ahead, negate that. And we should actually just form a, I guess, all of these intersections of such forth, given that X is going to be a universal set. And lastly, the finite unions of closed sets are closed. Oh, I should have actually, I just realized are going to be, this is going to be the other way around, which are going to be open. There we go. Of closed sets are closed. Cool. So let's go ahead and prove this theorem. Let's see. So as we've shown earlier, you give up. Hello. As we've shown earlier, both X and phi, or X and the empty set, are going to be closed themselves due to the sort of, I guess, relationship. And furthermore, the arbitrary intersections as well as the finite unions are kind of like the inverses of what was previously stated for open sets under arbitrary unions and finite intersections, subcollections of intersections, and I guess just negating them or taking the opposite of it. I guess more so stated the complement. So it's easy to show. All right. So it's jumping straight into a theorem closed in Y. Let Y be a subspace of X then A is closed in Y if and only if it equals an intersection of a closed set. Of X with targets with y. So let's actually just scroll up because I don't want to lose too much. So what does this really mean? So as long as we have some sort of relationship that a is going to be equal to some sort of closed set of x with y, so I guess like sort of that relationship, or if we cancel out x with a and a is going to be a subset of y, then it's going to be closed in y itself. So therefore we could actually just show that sort of relationship with x itself, or with a y that's closed in y, as long as this equality holds. So suppose that A is a intersection between some set E set or some set C intersected with Y, where C is closed in X. You got it? All right. Then X set minus C is open. Thus, X set minus C intersected with Y is open. However, this means Y set minus A is open in Y, thus A is closed in Y. So we go ahead and proved our first remark, so that's great. And our second remark is going to be conversely. Assume that A is closed in Y. So this is more so, I guess we went from right to left, but we're now going from left to right. So if this is the case, then Y set minus A is open. Hence, A is an intersection section of an open set of X closed in of X in Y with Y. Therefore, X set minus I guess we could just actually label intersection open set U in X. So let's just go ahead. So then therefore X set minus U is closed in X, and A is equal to Y intersected with X set minus U. And this is, we just kind of have to reinstate a new open set. We could have just done C, but is also closed in Y. Yeah. So I guess moving forward, we're gonna quickly define 3 different definitions to just finish out the rest of this chapter. And then maybe we'll go ahead into some, like, I guess, special content that I really want to look at. So the closure of X, I'm going to denote this either, you could either see them as X bar or CL of X. This is probably what I'm going to use a lot more, but you probably see this a lot more in the real world, is the smallest closed set containing X. And I prefer this definition compared to Munker's. I don't remember what Munker's definition was. I think Munker's was like closure is um, a set containing yeah. Is it really an algebraic moment? Maybe. But I think Munker's itself says like closure is like the set containing all of the closed I guess sets. I don't even know. It's not nice. There we go. Because like I mean sure you could contain all the closed sets, but I mean if it's not finite, if you have an infinite set, it's just it really doesn't look nice to have that as an absolute definition. That's my personal opinion, and this one makes it a lot more easier to I guess think about and like understand, I guess intuition wise. And not to mention, the later theorems become extremely obvious when you just think of it as the smallest closed set containing X. Um, and this also means there's, I think, literally a theorem saying, um, given that X itself is closed, what's the closure of X or something like that in the later part of Munker's? With this definition of closure, if X is closed, then it's obviously going to be itself. So that's not bad at all. And then furthermore, the interior, which I have never really seen be used, is I guess we're going to denote it sort of in similar fashion. Int x, the union of all open subsets of X. And I think the interior, I think some people, especially in like topology, I think might do this, or I actually don't know what the proper denotion is for interior. Oh God. Um, but I guess we're gonna stick with this one. And then lastly, we also have a limit point. Oh, you could write x in. Okay, yeah, perhaps. Um, and then finally the limit point. Uh, the exterior. What about the exterior boundary? We don't quite need to go into those quite yet. Maybe down the line. I don't even think Munkers has introduced boundaries or exteriors yet, so I think I withheld on that. But finally the limit point. I think also comparatively to Munkers, we're gonna do an analytical definition. So let A be a subset, so I'm just going to actually just use as much set notation as possible. Subset of an interval I, interval. X in I is a limit point of A if for all epsilon greater than 0, this sort of epsilon boundary, x plus epsilon, contains some point of A other than x. The closure is defined as the intersection of all closed sets containing x, and the statement, the smallest set containing. Yes, it is. They are absolutely equivalent. This is purely just due to intuition. Um, I mean, personally, I think this is a lot easier to think about, and it kind of makes a lot of the later theorems and like all the theorems concerning closure. In Is my Wi-Fi going out? I think my Wi-Fi is dying. Interesting. Um, Please tell me. Okay, cool. Fine. Okay. Hopefully that wasn't gone out too much. It's OBS said it was reconnecting or something like that, and that's kind of scary for me. But this is yeah, my stream is buffering. Gotcha. Um, Closure itself is purely just, or this definition of closure itself is purely intuitional. Makes the rest of Munkers quite redundant because it says there, I know there's definitely like a theorem right after this saying that like um, given x is closed, the closure is just equal to itself. And there's I think like one or two more theorems that are also just redundant if you just think about it smallest closed set and containing x, of course. And that's purely the best way to think about these sort of things. Um, but yeah, but what Rafid said, they are purely just equivalent. And in terms of intuition, I preferred this a lot more. Um, this sort of, I guess, behavior that we call here, we generally call it a neighborhood. And some may even say like a epsilon boundary. Epsilon boundary. Especially when you get to later, especially maybe like in analysis or I guess maybe in this course later on, I don't quite remember. You might deal with open balls. Actually, you definitely will deal with open balls. But sort of the same exact idea. Sort of this exact same idea of just an epsilon boundary or a neighborhood. And Munkers also uses like the words cluster points or points of accumulation, which I think is absolutely insane. I have never heard it called anything other than a limit point. Yeah, but I think I think that's really the extent that we're gonna get to. All right. So what we're gonna start is a new section called real induction. So real induction, this is really funny. This is actually made by Pete Clark, P.L. Clark, um, University of Georgia. Wait, bro, we need examples of closure, interior, and limit points. Um, I mean, do we really need examples? I mean, I guess for a limit point, let's take a 0 and 1 over n, or 0 to 1 over n. And so as whenever n gets small, then this itself is going to be closed, compact, and 0 is the li. That's like, I think that's the biggest example that most people know. So let's just take 0 to 1. So as we continue down this sort of list, so 1 half, 1/3, 1/4, we're always going to have some sort of epsilon boundary between 0 and we can technically go to -1, for example, that exists between this sort of range. So I'm going to go ahead and choose a different color. So actually just do red here. So if we choose red here, and red is going to be our epsilon boundary, actually red is going to be our epsilon boundary here, then we will in fact have some sort of element that will always lie between this sort of area, which shows that it's first off, it's closed because it contains all of its limit points. Secondly, it's compact. And 0 itself is going to also be a limit point of itself. we will actually define compact a little bit later, but this is a pretty well-known idea for it. So actually, I just forget about the fact that it says compact here, but these two are going to hold regardless. All right, perfect. So, let's take a look. So moving on into real induction territory, this was a topic introduced by Dr. Clark, Pete. And we generally always thought about induction and using like the natural numbers, so prove it's true for all n and n. And then now we're introducing a concept of real numbers, so this becomes a whole question itself in which Dr. Clark proved. So I guess let's go ahead and define inductive. So what does it mean to be inductive? You go ahead and take this phone call. Okay, sorry, we are back. So when we're defining what it means to be inductive, this is also going to be true itself for um, is also going to be true itself for even like the natural numbers. But generally, we always think about inductiveness in the real numbers as the form of what's going to be possible for these real numbers. And I guess like dependent on the order topology, we of course want some sort of ordering on these numbers. So let's go ahead and take a subset of a list of numbers that are going to be closed itself is inductive if for one, let's go ahead, label these as the real inductions axioms. So A is an S, that's going to have to be a given. Ri2, if A is less than or equal to X is less than B, then X is in S, thus X, Y is going to be in S for some Y greater than X. And last but not least, our last axiom for the real inductions, or I guess a sort of inductive set, is going to be if A is less than X, less than or equal to B, and A and X is going to be a subset, or you don't actually have to have it, is a subset of S, then X is in S. All right. So let's go ahead and see how this would look like in actual application. So let's go ahead and define a theorem, the real induction. For S is a subset of A to B, the following are equivalent. So S is inductive, and 2, S is going to be equal to A to B. Let's go ahead and prove this. Let's prove. So from going from the first to the second, it's easy to show if it's easy to show just I guess by contradiction how this can work out. So let's go ahead and let S be inductive to begin with. So let it be inductive. And then for the sake of contradiction, just suppose there's going to be some sort of set Q, which is going to be equal to A to B, and then just take out S itself, set minus S. So then if we take out set minus S, and we already know that S itself is already inductive, not to mention it's already a closed boundary itself, regardless of S being infinitely many points in A to B, or all of A to B, or just some parts of A to B, then if that's the case, we already have the infimum of Q established. Exists and is finite. And this is true because if we take a look at the axioms for inductiveness, we already have that A itself does exist in S, so all right, we've taken out A. We also have that there's some sort of set X to Y that's closed in S, so we've taken out a couple of those. And furthermore, we also have A to X is a subset of S, so we've taken out everything until perhaps something after X, maybe until Y. So that holds true. So everything until, say, like Y is going to be in, or I guess Y itself, or Y plus 1 is going to be the infimum of Q, supposedly. So I guess just running through that sort of mindset now. So if we go ahead and run case 1, infimum of Q is equal to A by the real induction 1, A is an S, and by the real induction axiom 2, there exists Y greater than A such that A to Y is an S, is a subset of S. Thus, Y is a GLB for Q, is equal to inf of Q. Thus, A is equal to, or I guess we should actually just denote these terms separately. Y is a GLB for Q. Thus, A equals inf Q, which is obviously not gonna be true. Our second case, so let's go ahead and define this as A is less than inf of Q. If inf of Q is going to be equal to B, and by S itself is going to be equal to A to B. Or else, by the real induction axiom 2, there exists y greater than infimum of q, such that inf of q to y is going to be a subset of S. And that's also going to be contradictory in nature. And lastly, our case 3 is going to have that A is less than the infimum of Q, which is going to be a subset or an element in S, which is going to be problematic of its own. And this immediately just implies that A to inf of Q is a subset of S, which is a problem. Perfect. Perfect. So I guess an application of this will be the Bolzano-Weierstrass. Bolzano-Weierstrass, which is a famous theorem that kind of shows convergence. But furthermore, it also is pivotal to show, I guess, Cauchy convergence and almost the entire basis for like metric spaces, as well as a large part of real analysis. But Bolzano-Weierstrass can be simplified to an extremely simple theorem. Every infinite subset of AB has a limit point in A to B. Now let's go ahead and prove this. So let A be an infinite subset of A to B, and S is the set of X. So S is the set of X in A to B, such that the intersection from A to X is infinite, implying it has a Li. Then it suffices to show that S itself is going to be equal to AB, but the way that we could do that is by real induction. So first off, let's go ahead through these axioms themselves. So by real induction, step 1, we just have to show that, we scroll up over here, we just have to show that A itself is going to be contained in S. And that is quite trivial, so that's always going to be given. And our step 2 is, actually we should probably go to step 3 first. So our axiom 3 is going to have it that since A intersection A to X is finite, if and only if A intersection A to X did I write that right? is actually just going to be S. S is intersected with eta x is finite. And then for the real induction 2, suppose x is an element in S if A intersection A to X is infinite, then it has a limit point. So because we don't want to go circle back over to the hypothesis, let's go ahead actually assume that A intersection A to X is infinite. Oh, I just realized what my mistake was. This was actually supposed to be A intersection A to B itself is going to be finite. So then let's just assume that A intersection A to X is actually finite. Then there exists either delta greater than 0, such that A intersection AX plus delta is finite, or for all, or I guess not for all, every x plus delta contains infinitely many points. Hence, X is an ally. And that's our proof for the Boltzano-Weierstrass, made a lot simpler with real induction. Does anyone have any questions, especially for something quite large like that? All right. All right, perfect. So let's go ahead, define compactness. And we sort of showed this, I guess, concept a little bit earlier, but a subset of R is compact if given any family ui for I and I open. This is going to be subsets of R. Open if A is a subset of this, I guess, union ui, then there exists a finite subset J subset of I such that A is a subset of J and J of these sort of finite subsets, or the union of these finite subsets. And I guess we could just go ahead and look at this sort of example, 1 over to n. If we see -1, -1, 0, if we go ahead and see this sort of 1/2 over here, then as much as we contain, um, I guess, infinitely many possibilities and values, we will still be able to count or have some sort of countable amount or finite many elements for a certain range. So if we go ahead, take I guess 0 all the way until 1/4, and then sort of intersect this with 0 to 1/2, then you will have finitely many points in this sort of area, which shows this sort of compactness here. And there would also be true for any sort of element within here. Let's go ahead and show a lemma. So given A compact, then A is bounded, and every Li is an element of A. Let's go prove this. So for n in the naturals, let u of n be equal to the negatives of this like sort of range. Then we also have it that if we have an infinite union, given that n is equal to 1, of un, then this would actually just contain, be all of R itself, and that's sort of the idea that we're working with here. And thus, every finite union of un is bounded. Suppose A is unbounded, then A is a subset of this sort of infinite union. And not contained in a finite boundary. So if in J subset of I, or I guess we don't even have it to have a subset of I, we could just be a subset of the natural numbers, and it's not contained in R n and J of U n. Suppose that we have an element A and A, Li, which doesn't lie in A. Or no, I should actually respecify this. Suppose A is an Li for A, such that A is not contained in A, which is possible. Then let un be all elements A minus 1 over n unionized with A plus 1 over n all the way to infinity. Then the union from n equals 1 of un is just going to be equal to the real numbers set minus A. So A can actually be contained in the natural numbers of un. But A is an Li of A. Hence, there is no final subset J with A being a subset of this infinite or this finite union. And I'm gonna take a quick second to see if anyone has any sort of questions here. All right. Okay, so this leads into the theorem that's really well known as Heine-Borel, which just says the interval a to b closed is compact. And this shows for an open covering, U, which is equal to this sort of family of sets, UI, of A to B, let S be defined by X in A to B, such that U intersected with A to B has a finite subcover. And then by real induction, Ri1 is clear. Ri2 follows if U1, UN covers A to X, then some UI contains X to X plus delta for some delta greater than 0. And then lastly, our third axiom follows if given A to X, which is a subset of S, and let I X be an element of this interval, such that X is in UIX, and delta is greater than 0, such that X minus delta to X is an element of this UIX. Since X minus delta is an element of S, then there is a finite J, which is a finite subcover, or a finite interval J, subset of the interval, with the union from I to J of UI is a superset of A to X minus delta. So UI, given i's in J, is a union with UIX covers AX. And this is our finite subcover. This will be our finite subcover. And that completes compactness. Should also probably do these here. All right. And we're finally reaching our final stretch over here. We just will be doing maybe like around 2 more theorem proofs after a definition, and then finally finish off with a couple of examples. So I'm gonna go off into Hausdorff spaces. And generally when we look at ordered sets, we could always tell what's going to be closed. So like for example, in R, we always have ordered sets that contain either an open boundary, A to B, some that are closed that will be A to B, or I guess this is actually going to be neither open or closed, and then some that are going to be closed like A to B, or A to infinity, as we've seen before. So these will always be, I guess, some sort of notion of open or closed, or even neither. But this may always not be true for arbitrary sets. So if we just have like I guess what the textbook mentions, we have an element B, which contains itself. And then we also have element A, or I guess we can actually just make this a little bit easier. So if we have B, which contains itself, and we have an element A, which also contains B, and we have an element C, which also contains B, then just because we remove this sort of B, I guess, point element, single point element, or single point sets, just because we remove that single point set around B, it doesn't mean that it's necessarily immediately open or closed. It kind of becomes a bit more ambiguous, and this would be an example of an arbitrary topological space, and this is sort of an example that we actually seen before. And of course, there's also notions of convergence, and Hausdorff also makes it so that we're only dealing with, I guess, reduces ambiguity for open / closed / neither sets, and also allows reduces multiple convergences. And to, I guess, think of that, that's kind of crazy because, like, for example, let's just say we have this set. Let's say that xn is going to be equal to b. Then it also happens to be the case that xn goes to A, goes to C. And this is an example of a multiple convergence. And it's sort of hard to think about. Oh, xn. Oh, there we go. Okay, nice. Xn goes to A and C. And this is kind of problematic, especially when we're considering convergence for more applicable areas. And we sort of always want to work with Hausdorff spaces, especially later in point set, or even if you're planning to go or already have studied real analysis. In real analysis, you probably just consider Cauchy sequences, or always said that they will always converge to one point, but that's always not true, especially in general topologies or some arbitrary topology. So let's go ahead and define what a Hausdorff space is. Dorff space. And generally, whenever you see people talking, you will just always see it referenced as just Hausdorff. Never seen it otherwise. So X top space is Hausdorff. I guess could capitalize this, Hausdorff. If for all x1 and x2 in X distinct, there exists U1 and U2 neighborhoods also disjoint. And I guess there's sort of an equivalent set notation for it. So given if x um, in u, y in v, and u, v, or I guess, yeah, actually, no, that'll be fine. If x is in u and y is in v, then u intersection with v is going to be distinct. And I think that's like the shorthand version of saying it. There's probably going to be more restrictions on it, though. I think Munkers actually does give the set notation equivalent for it, so no worries about that. So then we have a theorem that every finite point set in X Hausdorff is closed. And this reduces that sort of ambiguity that we sort of faced before, whereas just because we reduce this sort of one element, we don't even know if it's going to be closed or not, or open or not. And that's sort of that, I guess, problem that it goes as it tries to solve. So proof, if X is a point, so I guess I could just say this, if X is an X, X not equal to X not, and X is going to be in, or U and V distinct, such that X is in U, X not is in V. Since U doesn't intersect with does not intersect with X not, then hey there, welcome from Bulgaria. Then X cannot be in the closure. Cannot be in the closure of X naught. Hence, X naught closure is itself. You finished your book on calculus of variations? That's funny. I've actually seen many books recently, in recent times, especially this semester, on calculus of variation. It seems to be the almost leading topic in today's studies. And we could actually go into a second theorem. So if X Hausdorff, then every sequence of X converges to, at most, 1 point in X. So proof, suppose xn sequence in X that converges to X if y is not equal to X, u, v disjoint neighborhoods, since U contains X, and for all but finitely many, and this is based off our notion of what convergence is, finitely many values of n, then V cannot. Hence, xn cannot converge to y. And that tracks. I guess we have a sort of proposition, or not a, I guess we could say it's a proposition that ordered sets product of two Hausdorff spaces and a subspace of Hausdorff is Hausdorff. And then we also have another proposition that if X finite Hausdorff top space, then it is discrete. Whew. And then we could actually see examples of such here. So the trivial topology, so if we just have X is equal, or ta is going to be equal to the set of the empty set and X, which is just trivial, not Hausdorff, for X greater than 2. And we also have another example that the finite complement and actually I think it's denoted by this finite complement and the countable topologies are not Hausdorff. And that's actually built upon the same exact idea. All right. Yeah. And actually, I shouldn't say it's the same exact idea, but it's because these are finite Hausdorff spaces, but not discrete. And this one is just because it's less than 2. Yeah. All right. And that finishes today's lecture. Does anyone have any questions? All right. Well, thank you for joining today. Lectures will be posted later today, hopefully. So, all right. Have a good day. Bye-bye.